What's up, smart people? Welcome back or welcome to this YouTube channel if you are new here today. So, if you click on this YouTube video, I believe you're up for a challenge to derive x function of simple harmonic motion using differential equation.
Oh my god, bro.
Oh, hell no.
But if that was not your reason, or perhaps you clicked it for fun, no worries, I'll make sure you end this video strong, okay? And I'll make sure you have a lot of fun throughout this video.
That's suspicious.
Okay, so I'm actually really excited for today's video. And also, on a side note, this is not in physics Cambridge A-level syllabus. But it's really an interesting fact to know. Trust me. When I say it's fun, it's actually fun. Okay, so we will see about it, okay? It's actually fun. So without further ado, let's get started. Okay, to begin with, let me draw a beautiful spring. Attached to the wall, you have a spring here, you have a load, you have equilibrium position here. Okay, so now, in episode 1, I know right, episode 1 is seems like a long time ago, but anyways, in episode 1, we learned that we have something called the restoring force, and if the spring is, example, you put the load and you pull the spring this side, so where will the restoring force will be acting, or the spring force will be acting? Basically towards the equilibrium. Am I right? And since there is no weight here, not to say there's no weight, the weight is not involved in the direction we are looking at, because we're looking at the x direction and the weight is not involved there. Therefore, our resultant force is equal to our spring force, which is our restoring force also. So if I were to write it, our F net equals to F subscript S, which is indicating the spring force. Therefore, okay, let me write this down here because you might need to use a space there later. F net equals to Fs. Net is the resultant force, and we know it's Ma equals to negative Kx. Remember, don't forget you're negative. I have explained why in episode 1, negative is really crucial. So, if you're wondering, you can watch episode 1 back if you haven't watched. Okay. Anyways, okay, so M, is there a way we can, transform this to a differential equation form? So, actually there is. Because we know A is d2x dt square. Now, I know you might be thinking, why out of everything I choose d2x and dt square? Why can't I take dv dt? Because we have x here. So I'm trying to match the variable. That is why I choose d2x and dt square. Okay, now let's rearrange this equation a little bit. So m d2x, we bring everything to the left hand side, okay, plus kx equals to 0. Now let's multiply the entire equation by 1 over m. I'm going to put a note here. Multiply the equation by 1 over m, or divide it, in other words, simple words is divide it by 1 over m. You will get d2x dt squared plus k over m x equals to 0. In the previous video, we actually discussed on what k over m is, and we know k over m is actually omega squared. So let's refine this equation. Oh my god, the 2 is so big. Refine this equation by rewriting it with omega square x equals to 0. Now, what is this equation? Is it familiar to you? Yes, we have reached to the first type of differential equation. This is actually second order homogeneous. I know, right? It's such a long name. Differential equation. Okay, I'm just going to write it as DE. I'm not going to write the entire thing, it's too long. Second order homogeneous differential equation. Why is it homogeneous? Because my right side of my equation is 0. That's why it's called as homogeneous. Okay. Now, in general, we know that the solution to this equation in general is actually x equals to ae lambda, not lambda, down, to the power of lambda t. Okay, now I know you might be thinking, wait, why suddenly got lambda here, why got a here? Okay, no worries. So before we solve second order differential equation there, you will find it helpful to look at the form of the first order linear homogeneous differential equation with constant coefficient. So in general, we have, let's say, I'm not going to put dy dx, I'm going to use dx dt instead because we are looking at that here, right? dx dt. dx dt plus, let's say, kx equals to 0. This is the normal differential equation that we have here. It's actually of this form. It's just that this is second order and this is first order. That's the difference. So I'm going to explain to you using first order because I believe it will help you. So how do we solve this? We solve this by separating the variable, right? So first we bring it to the left hand side. Then we separate the variable equals to negative k dt. Now what do? We integrate. Am I right? So this will give me ln modulus x negative kt plus c. C is my constant. So x equals to e negative kt plus c. I'm going to rewrite this as ec e negative kt. This is actually indices law because anything like any power that is plus here, you can actually separate it by a product form, right? Okay. Now, open up modulus, you'll get positive negative ec e negative kt.
Hey.
So what I'm going to do now is I'm going to rewrite this with a constant where a is equals to positive negative ec. So that is why I say in general this is the form of the equation. So the solution of any first order equation of this type, of this particular type. So what is this type? So this actually shows that the explanation to this equation shows that the rate of change of x is directly proportional to the change in x itself. Now we add a constant to solve, we add the constant k to solve the equation, right? So yeah, so any equation of this form will contain exponential function and an unknown constant, or you call it as arbitrary constant. So with this being said, knowing the form of the solution actually allows you to find it without doing any integration. So what do I mean? Okay, so now we know that, okay, coming back to the second order homogeneous differential equation just now, I said we have already discussed y is x equals to ae power of lambda t, right? Now let's find what is dx dt, basically the first derivative of x. You know it's lambda ae lambda t, just normal differentiation. You differentiate twice again, you get lambda square ae lambda t. Okay, so what are we going to do now? We're going to sub these values that we have inside this equation. So when we sub in, what do we get? So let's sub in lambda square ae lambda t, because the first one is the second derivative, plus omega square. It's advisable to use bracket here because you're dealing with a lot of constant. And also stay calm. Okay, just stay calm. I know there's a lot of letters here and you realize there's no numbers here, right? For some reason it's maths but there's no numbers. It's okay, just stay calm and you'll be fine, okay? Just do it slowly. Imagine you are dealing with numbers, but it's just some random letters here. Okay, so now I realize that these two are common, so I'm going to factor it out. So ae lambda t being factored out, I am left with lambda square plus omega square equals to 0. So I would eventually get lambda square plus omega square equals to 0. Okay, because e lambda t is never equal to 0. Exponential function is never equal to 0. And in this case a, we are not taking a as a value of 0, because I understand the trivial solution, there's a possibility to have a trivial solution that the a is 0. But for this case, solving x function, let's take the non-trivial equation instead. It would actually guide us to get the equation. Yeah. So therefore, we are stating the fact that a is not 0 for this case. Yeah. Okay. But yeah, there is a trivial solution which is 0. But for this case, we're not taking that. because we are trying to get the equation. Therefore, it's best to for a while we not take the trivial solution in. Yep. Okay, so we get this, right? Then let's solve for lambda now. It will get lambda equals to positive negative square root negative omega squared. And we know anything with a cert or square root negative, we can write it as imaginary number. So you'll get positive negative omega I. So that just means your x is either AE omega I. Okay, let me use AE omega IT, and your x can also be BE negative omega IT. Why I use B here? If it's a second order differential equation, you have actually two arbitrary constant. If it's first order, then you only have one arbitrary constant. So the number of arbitrary constant in the solution is actually equal to the order of the differential equation. You have third order, means you got three constants one. Okay. Alright, now we have these two solutions. So what are we going to do with it? Where are we heading? Okay. What are we going to do is, we're going to take a general solution from these two. That means we're going to have something called as the complementary function. So the name itself, it's complementary function. So complementary function means it complements all types of solution for the second order differential equation. Because if I just said x equals to, okay, for example, my x is A is 7, B is 8. So I'm trying to tell you, okay, for this equation, for this second order equation, these are my solution. But we know these solutions are only based on the initial condition given, right? But if a different condition is given, you're going to get a different value. So what we do, we provide a complementary function, a general function, so that any value that is sub into this function will give you a solution. Because second order differential equation has infinitely many number of solutions depending on your condition. So just saying, oh, it has this only as your solution is not a complete. So we find the complementary function to provide a complete solution. Okay, alright. So what is the complementary function? The complementary function is basically x equals to, we add them up together. Yeah, that will be your complementary function. I know you might be wondering, so if we add this up, when we substitute inside our homogeneous equation, will we still get 0? Yes, you will still get 0. You can try and see, and you will definitely still get 0. Yeah, so this is the complete form of the equation. Okay, alright. Now, this is where we use a teeny bit of complex number knowledge. Okay, so we call Euler's, okay, I'm not sure how to pronounce this. Is it Euler's or Euler's identity? Anyways, it's an identity in complex number. Okay, it's an identity in complex number where cos theta plus I sin theta equals to EI theta. Right? Is it? Am I right? And if you realize, this form is almost similar to this form here. This both form here. It's very, very similar. Okay, so let me write this. Okay, I think we should perhaps go to the other side. Okay, use a different color as well. Okay, let me write this. So we know that lambda is given by omega I, and we have lambda equals, lambda equals to negative omega I, where our x, of first x, we have AE. I'm going to rewrite this as omega Ti. So if you realize, your theta is actually omega t. So now we can write the equation in terms of cos and sine. So x is equals to A, I'm going to open a big bracket here, A cos omega t plus I sine omega t. Okay, this is our first one. Then we have also x equals to AE negative omega t I. Our theta in this case is negative omega t. So let's rewrite it. A cos negative omega t plus I sine negative omega t. Okay. Cos can suck out the negative, right? And for sine, we can bring out the negative. So we will get negative, oh wait, cos suck out, right? So don't have negative. Omega t minus I sine omega t. Okay, now since our complementary function, we add both of them. So let's, okay, let me write this as our final form of CF, which is the complementary function. I just write it as short form. Okay, so x equals to A cos omega t plus I sine omega t, right? Because that's our first x here. Then plus the second A, wait a minute. Okay, I just realized the mistake. I'm not sure if you realize it or not. This is not A. It's supposed to be B, right? Yeah, I'm sorry. It's supposed to be B. Sorry. Please don't come at me. It's B. Sorry. Okay. Cos omega t minus I sine omega t. Okay, remember, we have to have two different constants, A and B, because we are dealing with second order differential equation. It's always consistent. The constants, arbitrary constants, are always consistent with the order of differential equation. First order only got one constant. That is why first order we only have one constant, A only. Now in this case, if it's second order, we have two constants. So in this case, I name it as A and B. Okay, alright. Now, what we can do is, we can group the variables. Have cos omega t here, cos omega t here. We have sine omega t here, sine omega t here. Can we do something? Yes, we definitely can do a lot of things with this. Okay, let's group them. A plus B cos omega t. Okay, then we have plus A minus B sine omega t. Okay, because we have A cos B here, open up, B cos omega t. Then we have A sine omega t. Don't forget your imaginary symbol. Then you have, oops, sorry. Then when you open up your B here, you get negative B I sine omega t. Remember, negative, positive, be careful. It can actually cause a lot of things in your equation. So be careful. So now what I want to do is, I want to try to rename this A and B. But what I want to do before that is, let's bring in the imaginary number inside the function. That means I'm going to write it as AI minus BI, so that I can name it together. Because we don't want to have imaginary numbers in our x function when we are doing for simple harmonic motion, right? Okay. So now, I'm going to rewrite this, the grand equation. Okay, let's use a color to show that it's the final equation. X equals to P cos omega t plus Q sine omega t, where it's always important to mention what your P is and your Q is, because you have renamed them, right? Q is AI minus BI. Okay, so I'll highlight for you so that you can see. A plus B is your P, AI minus BI is your Q. Okay, now let's start the physics. Finally, you realize, right, at this part there's usually no physics yet. It's only the first part Then it's all maths all the way along. And now we can use some of our physics knowledge, because we need to set the conditions right for you to solve. Because this is just a general solution. This is just the general solution, your complementary function, like any value can be in. Now we're going to set some conditions. We're going to give some values to come up with the x function. We're almost there. We're almost like, I think we are like 80% there already. Okay, so I'm just going to write the main equation here on the side below here, just in case we need to use it. Okay, so what I'm going to do is I'm going to set my condition as this. Okay, when, wait, this color is too light, man. Okay, when x equals to x naught and it's at t equals to 0, my velocity is v naught. This is my condition. I'm setting this as a condition, like as a value. So before I proceed further, I'm gonna explain to you first. This x naught, I do not mean it as amplitude in this case, because if I'm trying to say in this case, if my x naught as the amplitude, my v is supposed to be 0 here. So I know you might be thinking, so why can't I just put it 0? If I put it 0 here, it will be a bit challenging to derive the equation. You won't get the full form of the equation because you don't have that much enough of information. When the spring is oscillating, this is the wall, right? This is my spring. So at this point, it is x naught and it is t equals to 0 and it is moving at a velocity of v naught. Yeah, that's it. I then say this is my amplitude, this is my highest point. No, I'm just saying when it is oscillating, for example, I freeze the motion of my spring and it was at x naught and it was moving at the velocity of v naught, and in that time it's actually t equals to 0. Okay, we know our x is x naught, so x naught equals to p, that's what we're trying to find, cos t is equal to 0, okay, plus q sine t is 0. Sine 0 is 0, cos 0 gives you 1. So x naught equals to p. So we have found our p value. So let us rewrite it. X equals to x naught cos omega t plus q sine omega t. Okay, now next mission is to find what is our q. Okay, to do this, let's do some differentiation again. It's not a very big differentiation, it's a very chill differentiation. So what I'm going to do is, let's differentiate this equation. Or you can choose to differentiate this equation also. Actually, it's up to you. Okay, you know what? Let's differentiate this equation. X prime equals to p omega sine omega t negative. Remember, because you differentiate cos, you get negative sine omega t. Differentiate the one in bracket, you get omega. Okay. Plus q omega cos omega t. Okay. Now, let's rewrite this back. So if we rewrite this will be velocity. Now I know you might be thinking, why suddenly got velocity here? Because you differentiate your x function, it is dx dt. And dx dt is velocity, am I right? So I'm writing it as velocity equals to negative p, we know already, which is x naught, right? X naught omega sine omega t plus q, which is we are going to find in a while. So this is our equation, updated equation. Okay, now let's solve for q. What is V? We know V is V naught negative x naught omega sine omega t 0, because your t is 0, plus q omega cos 0. Now I know you might be thinking why I didn't use this equation to actually solve it, because I don't have that much of information to just use this equation. That's why I differentiate the complementary function to make use and find my what do we call my q as a constant. Okay, so v naught, when we rearrange this, sine 0 is officially 0, cos 0 is 1, give you q omega. Q equals to v naught omega. You got your q already. Now the final equation, basically your particular solution, is x equals to x naught cos omega t plus v naught omega sine omega t. Also, I'm reminding you again, my condition here, my x naught is not an amplitude. I'm just having a motion of my spring. Then I stop my spring, I see, oh, it's at x naught and it's time t equals 0 and my velocity is v naught. That's it. I'm not trying to say my x naught here is like my highest point. I'm not trying to say like in this particular condition my x naught means my highest point, because if it's the highest point my v has to be 0. But no, I'm just taking a random position as x naught. Okay, so now we have this equation, but then our x function is always just x cos, or I mean a cos omega t or a sin omega t, right? So how do we get that? Okay, no worries. When it's cos omega t, that means it started at the highest point. When our function of x is cos omega t, started at the highest point. Highest point means our velocity is, because you are away from your equilibrium position. When you're away from your equilibrium position, so you go away from your equilibrium position, your v is actually 0. That is so big. Your v is actually 0. And your a is at the maximum. At equilibrium position, your v is maximum, but your a is 0. Same goes to the most furthest position. A is maximum, v is 0. Because the further you are from the equilibrium position, you need more restoring force to restore it back, right? That is why your acceleration is maximum. And when there is no change in acceleration, basically the acceleration is max, it's like the maximum point, your velocity is 0, because acceleration is the rate of change of velocity. Velocity is 0. When you are at the equilibrium position, your acceleration is 0. You don't need acceleration because you're already at that point. You don't need to restore anything, right? Yeah. So coming back, if you want to get cos, that means our graph will look like this, right? That means we're trying to say that the spring started at, we're trying to say the motion of the spring from the highest point, which is from the amplitude. So highest point, amplitude, your x is equals to a. What will happen to your v? Your v will be equivalent to 0. So using this condition, what will we get? We will get x equals to your, sorry, this is your x naught, yeah? Your x naught is a cos omega t. This whole thing will be 0 because your v naught is 0. Your v naught is 0. Yep. Yeah. So if let's say I set my x naught to have a value of 3, my v naught is maybe 5, you just sub in, you will get a particular solution. You get a specific solution based on the condition. So this can vary, right? That is why we have to have a complementary function, because there are just infinitely number of solutions for you to come to this point. Yep. Now how about sine? So you want to get sine graph, that means it must start at the equilibrium. Equilibrium means your x naught is 0, right? So when your x naught is 0, your v has a value. Your v naught is basically v max, or it has a certain value because it's just at the equilibrium. This whole thing will be 0. Why? Because x naught is 0. So you will get x equals to v max over omega sine omega t. If you compute this, if there's, let's say in the equation they gave you, not equation, in the situation they gave you a value for maximum velocity and the omega, you will actually get this when you, after you calculate, you will actually get your amplitude value. That's about it for today's video. Today's video is actually quite long. I think it's almost 30 minutes plus. Yeah, so be patient in watching it. I actually break it down step by step so that it's clear for you to understand and you don't get confused a lot. But still, if you have any question, don't hesitate to ask me in the comments. I'll always do my very best to help you answer them. To do calculus or to solve any maths equation, realize until here there's no number, right, besides the 0 here. You need a lot of patience and calmness because you're dealing with a lot of variables. So you need to do it slow and steady. My advice to you is just stay calm, and I hope you enjoy them. And if it helps you, don't forget to like, share and subscribe. I'll see you in the next one. Bye bye.